Before LEDs took over, nearly every light bulb in the world relied on a metal thinner than a human hair, glowing white-hot at temperatures hot enough to melt steel, yet refusing to break, bend, or melt itself. Every time you flipped that switch, that tiny filament reached nearly 2,500 degrees Celsius in seconds. That metal was tungsten, the most heat-resistant metal ever discovered. Tungsten melts at 3,422 degrees Celsius, or about 6,192 degrees Fahrenheit. Iron melts at 1,538. Aluminum gives up at just 660. Most lava flows sit between 700 and 1,200 degrees. Tungsten would sit in lava and not even flinch. Among true metals, it stands completely alone. So what makes it so resistant to heat? The answer is in its atomic structure. Tungsten has the chemical symbol W, a holdover from its original name wolfram, and atomic number 74. It belongs to a group called refractory metals, defined by exceptional resistance to heat and wear. But even among that group, tungsten is in a league of its own. It can survive extreme heat because its atoms are held together incredibly tightly. Its outer electrons create some of the strongest bonds found in any metal, so it takes a huge amount of energy to pull those atoms apart, which is basically what melting means. On top of that, the atoms are packed into a very strong, dense crystal structure, almost like a tightly locked 3D grid, making the metal even harder to break down under heat. Combined with its heavy, dense nature, about as dense as gold. This is what makes tungsten the most heat-resistant metal on Earth. Tungsten also has one of the highest cohesive energies of any metal. Its very low vapor pressure means it barely evaporates even at extreme temperatures. The name tungsten comes from the Swedish words tungsten, meaning heavy stone, a reference to the dense mineral scheelite, where it was first identified. In 1781, Swedish chemist Carl Wilhelm Scheele extracted a new acid from scheelite and suspected it contained an unknown metal. He and his colleague Torbern Bergman theorized it could be reduced into a new element, but lacked the equipment to finish the job. In 1783, Spanish brothers Juan José and Fausto El Huyar picked up where Scheele left off. Working at the Royal Basque Society in Bergara, Spain, they mixed tungstic acid with charcoal, applied intense heat, and produced tiny gray metallic particles, the world's first isolated tungsten. For most of the following century, tungsten remained a scientific curiosity. It was brittle at room temperature and difficult to melt. Then came the light bulb. Early incandescent bulbs used carbon filaments, which were fragile, inefficient, and burned out quickly. Tungsten was the obvious candidate for something better. It had the highest melting point of any metal, a brilliant white-hot glow and low vapor pressure that kept it from evaporating inside the bulb. The problem was making it into wire. Pure tungsten was so brittle that any attempt to draw it into a filament snapped it immediately. The breakthrough came from American scientist William D. Coolidge, working at General Electric in Schenectady, New York. After years of trial and error, Coolidge developed a method to process tungsten powder into a form that could be drawn into flexible wire, thin enough to coil inside a bulb and strong enough to survive repeated heating and cooling cycles. By 1910, the process was refined, and tungsten filaments went on to dominate incandescent lighting for over a century. Once engineers understood what tungsten could do, they put it wherever extreme heat was a problem. Rocket nozzles, welding electrodes, high-temperature industrial furnaces, X-ray tubes. In the form of tungsten carbide, a compound nearly as hard as diamond, it became the material of choice for cutting tools, drill bits, and mining equipment. About half of all tungsten produced today goes into tungsten carbide alone. Nuclear fusion requires containing plasma at temperatures exceeding 100 million degrees Celsius inside a reactor. The walls of those reactors face punishment unlike anything in conventional engineering. Tungsten has been selected as the plasma-facing material for ITER, the world's largest fusion experiment currently under construction in southern France. Its heat resistance, low erosion, and very low retention of radioactive hydrogen isotopes make it the best material available for that role.